Our speaker today is Guy Moshkovitz, and he will be talking about maximizing projections.
Thank you. And thank you for having me, and hopefully no more technical issues. So this is based on joint work with Noga, Alon, and Noam Solomon. And indeed, it's a talk about projections. So it makes sense to start with a slide explaining what is a projection. So I'm going to use the most basic, most purely combinatorial notion of projection that you can think of. So I'm talking about the objects I'm talking about are the object is a family of sets or a collection of subsets. And in this case, for the drawing, I put those sets as in the rows of this matrix. Okay, so you can think of each row as specifying a set. Each row is a binary vector. And so this would be my collection of sets, my family of sets. And if I project onto, say, coordinates 1, 3, and 4, that just means that I just retain those coordinates and I forget about all the other columns. So in essence, I'm just erasing column number 2. I'm getting a new family, but now, of course, I might have repetitions. So we say that there are 5 projections on this set of 3 coordinates. Okay, you can count for yourself. Can you see the yellow markings, by the way?
Yes.
Thank you. So here is 1, here is 2, here is 3. This is a repetition, another one, and another repetition. So overall, I have 5 out of the possible 8 binary strings, so 8 sets over 3 elements. And that's it. By the way, of course, 8 is an obvious upper bound on the number of projections, but there was actually a slightly better upper bound in this case because the original family had 7 rows to begin with, you can count. So obviously when you project, no matter on which coordinate, you're going to see at most 7 distinct projections. Okay, so you always have these 2 trivial upper bounds on the number of projections, either 2 to the number of coordinates or just the original number of rows. Okay, so hopefully everyone understands what a projection is. Okay, and so now let's talk about the question here. So from now on, F will denote a family of binary vectors or a family of sets or a collection of subsets, or call it whatever you want. N is going to be the size of the universe. And this is the kind of extremal theorem that we're interested at. So the theorem would say something like every family of sets that's large enough necessarily have some k coordinates so that if you project on them, you have a lot of projections. Okay? It makes intuitive sense. The larger the family is, right, the more subsets you have, the more likely you are to find a large projection, a set P of coordinates that yield a lot of projections. The most famous example of such a meta theorem is, of course, the Sauer-Perles-Shelah Lemma or the Sauer-Perles-Shelah Lemma. And I will talk about this in more detail in 2 minutes maybe, but let me just read out the statement. So it's of the same general form. Every family of sets whose size is greater than the sum of the first k binomial coefficients. So that's n choose 0 plus n choose 1, dot, 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 n choose k minus 1. So if you have more than this many sets in your family, then there is necessarily a p, a set of coordinates, a set of k coordinates, so that if you project on that p, you're going to see all the possible 2 to the k projections. Okay, so in fact, this bound is actually equality. That's the maximum possible. We sometimes say, I don't know, I think in statistics or machine learning, they usually refer to such a set P as a shattering set. We said that the family is shattered, right? You see all possible, when you project on that P, you see all possibilities, all possible strings, all possible sets. And so the question we're asking, the meta question, is to bound this. So is to bound the following extremal quantity, which just stands for what is the best value you can put after this inequality in the meta theorem. So what are we talking about here? Let's try to parse it. Inside the maximization, this tells us that we're taking the best choice of k coordinates, okay, the best choice for f. And we're minimizing over all possible families with enough sets. So a lower bound of this quantity pi sub n of mk, would mean what? That we are guaranteed to find, so the best choice of p, the best choice of k coordinates, gives you at least something, that many projections. You are guaranteed, no matter the family, okay? As long as your family is large enough, the best choice of p, best choice of k coordinates would give you this many projections. That's a lower bound. An upper bound is the opposite. So that would mean that the best choice of coordinates can only give you so much projections. Okay, there is some family f for which even the best choice doesn't give too many projections. So in the first part of the talk, I will survey some classical results on this quantity and also prove a new upper bound on this. And then the second part of the talk would be a more challenging lower bound, also a new result. Okay. By the way, feel free to stop me at any point. I think the basic definition, we've covered it now. And but if something is not completely clear, then ask now, because otherwise it will get more complicated. Okay. So this function pi, as you would expect from such a fundamental quantity, basic quantity, it has a lot of applications in statistics, machine learning, and geometry, and more. And actually determining it for arbitrary values of the parameters n, m, and k. I'm reminding you that n is the size of the universe, m is the number of sets in f, and k is the number of coordinates that you project on. So actually determining this external quantity is hopeless. It's hopelessly hard, and I'm going to try to convince you of that. But just a moment before that, let me give you another example just to solidify a certain point. Suppose that this is your f. So this f has 5 sets, the empty sets, the singleton 1, the singleton 2, the singleton 3, the singleton 4. Okay, so it has m rows, one for each set in f, and n columns, one for each element of the universe. And notice that, say, if I project this f onto the last 2 coordinates, so I'm getting this guy, you can check for yourself, which has 3 projections, right? 3 distinct rows, 0, 0, 1, 0, 0, 1. Of course, it's missing the 1, 1. So here's a question for you. Is there a better choice for 2 coordinates? Can I get more? Can I choose 2 other coordinates so that if I project on them, I get more than 3 projections? Right. So the answer is no. Yeah, go ahead.
Yeah, I just said no.
Fantastic. So, and then the simple reason is that if there was such choice, then you would have 4 projections. 4 projections is the maximum possible. So in particular, you would have 1, 1 as a projection. But that can't be, because even the original f didn't have a row with 2 1s, right? So you're just never going to get 1, 1 as a projection. So at most 3 projections that's the most you can hope for. And in fact, if you add, it's easy to see that if you start from this f and add any other row, then you will be able to make a smart choice of 2 coordinates that would give you all 4 projections, for the obvious reason that if you want to add a new row, which is distinct from all the others, then it will have to have 2 1s, and then you'll just project on those 2 coordinates. Okay, but of course you might ask, okay, but what if I don't start with this particular f? So this f has 5 rows, 5 sets. Is it true that any 6 sets would necessarily have 4 projections on some pair of coordinates? The answer is yes, and this is exactly the content of the Sauer-Perles-Shelah Lemma that I mentioned before. So let me kind of more slowly cover it. If n is greater than the sum of the first k binomial coefficients, in our case, in the previous example where k was 2, we were talking about projecting on 2 coordinates, then this sum is n choose 0 plus n choose 1, and that's it. So 1 plus n. 1 plus n in this case is 5. So if you have more than 5 sets, then you are guaranteed that pi is actually the maximum. We have complete shattering. And actually, if you want complete shattering, the maximum 2 to the k choices, then projections, sorry, then this is the tight bound. Because if m is not strictly larger than the sum of the first k binomial coefficients, then this is not guaranteed. And we saw an example just this in the previous slide, right? You just take all rows with less than k ones. So obviously you won't get the 1, 1, 1 projection. Okay, so that's this classical Sauer-Perles-Shelah lemma. Tons of applications, very important. But then you might ask, okay, this question is completely settled. The question of when do we get full projection? When do we get 2 to the k projections? What if we just want to ask what m guarantees 2 to the k, say minus 1 projections? Okay, mild alteration of the question. Well, this is already a wide open question. So let me try to convince you of that. Well, if you take the very particular case of k equals 3, then actually this is solved. And here's the point. So Alon and Frankel both observed that you can assume without loss of generality that your family is monotone. So if it contains a set, then it also contains all its subsets. Or if this matrix contains a vector, then it contains all the vectors obtained by removing ones and turning them into zeros. Okay, so which means that if you just want, so that means that if you have a projection of 1, 1, 1 on some 3 coordinates, then you have all the projections below 1, 1, 1. Okay, so you will have all 8 projections. So if you just want 7 projections, then without loss of generality, you can assume that no row has 3 ones. So that means every row has at most 2 ones. But now it becomes a question in graph theory, essentially, right? Identify each row, which has at most 2 ones, with an edge in a graph. So the graph would have n vertices, 1 per each column. And if you have a row with 1 at the ith entry and the jth entry, then you would have an edge connecting vertex I and vertex j. And 3 coordinates would give you all 7 projections. In particular means that you would, on those 3 coordinates, you will get 1, 0, 0, 0, oh, sorry, 1, 1, 0, 1, 0, 1, 0, 1, 1. So all the choices of 2 out of the 3 coordinates being 1, which in graph terms, in the terms of the graph that we just mentioned, this is just a complete graph on 3 vertices. This is a triangle. And now Mendel's theorem completes this theorem, just saying that we know exactly what's the extremal number what number of edges in a graph guarantee a triangle. Okay, so the result here up to lower order terms is exactly that. So and Mendel's theorem tells you that the optimal answer is 1/2 of what is the Sauer-Shelah bound. Okay, the external construction here would be basically a complete bipartite graph. Okay, so fantastic. We know the smallest m that guarantees 7 projections on 3 coordinates. What about the next case, k equals 4? So by the same logic that I just mentioned, this is equivalent to the Turan's conjecture on the extremal number of complete 3 uniform hypergraph on 4 vertices. Okay, which is infamously open. The conjecture is that the right answer should be 5/9 times the Sauer-Shelah bound. This would be tight if true. And that's a long-standing open question. No hope of solving this with current technology, I guess. So what I'm trying to say here is that even if k is very small, say k equals 4, you already get an open question. So I'm not going to go this route. Instead, I'm going to consider the complementary setting. We're going to talk about projections on a linear number of coordinates, half of the coordinates, quarter of the coordinates, okay? Maybe there's hope to say something here. Okay, so if you kind of didn't follow the previous slide, you can just completely forget that, because from now on, we only care about the setting of projecting on a large number of coordinates, not just 2, 3, 4 coordinates, but theta of n coordinates. Okay. So actually, there are still classical results here, but those results assume that your family is very large, that the number of sets in your family, M, is on the order of 2 to the n, which is the maximum you can open, like maybe 1/10 of 2 to the n. Under that assumption, there's a whole body of work, mostly in computer science, related to the influence of Boolean functions, that is mostly just a rephrasing of this question in that setting. So first thing to notice is that if your family is that large, if you contain an exponential number of sets, then the question isn't interesting if you're projecting on less than half of the coordinates, just by Sauer-Shelah, right? Because then the first, say, 0.49n binomial coefficients, this is still a sub-exponential number, so the number of sets is larger than that. And then so Sauer-Shelah guarantees, 49% of the coordinates that give you full projection. Okay, so really the only interesting question here is what happens if you project on more than half of the coordinates. So there's the famous Kahn-Kalai-Linial KKL result, which gives this bound, which is close to the maximum 2 to the k. So 1 minus some small quantity times 2 to the k. So he almost gives you all possible projections, but not all of them. But importantly, this assumes that the family is large, exponentially sized. I'm not going to go in depth here. I'll just mention that there was a lot of work here around these questions. There was a conjecture that maybe this error term can be improved from polynomial in n to exponentially small in n. This was refuted by a more recent paper by Baruch and Kahn-Kalai. So bottom line here is that, so this is nearly tight. So the bottom line is that if your family is large, is exponentially sized, then the external question of pi is basically solved, roughly. Okay. Okay. So excellent. For very large families, the problem is solved. What about everything else? What about the case where m is not necessarily exponential in size? It's not a huge family. Turns out that in this case, you get a completely different behavior for this question. So this brings us to our setting. And notice that in our setting where m is not exponential, then the trivial upper bound is not 2 to the k, right? So far, all the results that we mentioned compare the number of projections to the maximum 2 to the k, right? But now if m is sub-exponential, then there is a better trivial upper bound, which, by the way, I've mentioned in the first slide of this talk. M is a better trivial upper bound than 2 to the k simply because k is linear. So 2 to the k is exponential, and we said that m is not exponential, sub-exponential. So the enemy, what we're fighting against, the bound that we're trying to beat, is the trivial m as the number of projections. So in fact, there were some results known, and at least for the case where m is polynomial. So m is very small, maybe n to the 10, this kind of size, n to some constant. So that was by Bolenbach and Radcliffe. And let me exemplify just for concreteness, exemplify the result for the particular interesting case where m is n squared and k is 1/2 of the coordinates. Okay, so we're talking about n squared sets over a universe of size n, and we're projecting on half of the coordinates, and we're asking what's the best projection? What's the best choice of coordinates that would give us the most projections? So they proved, well, the upper bound they proved is little over n squared, Okay, so asymptotically smaller than m. Okay, so they showed that interestingly, as opposed to Sauer-Shelah and all the other lemmas that we saw, or the other known results, you can't actually hope to get order m many projections, even with the best choice of coordinates, of n over 2 coordinates. You just can't get, a fraction of the entire family. And on the other side, on the lower bound side, they gave actually a way to choose n over 2 coordinates to project on that would give you n to the power of roughly 1.17 or so. Okay, so they show that there is a choice of n over 2 coordinates, so that if you project on them, no matter your family, as long as the family is of size n squared, you're going to get n to the 1.17. Okay, of course, the lower bound would be trivially a number between n and n squared. They were able to obtain n to the 1.17. Okay, so now we can mention our results. And first I'm going to, so our results actually don't hold just for sets of families of polynomial size, but actually much more general than families than that. But for concreteness, let me exemplify, to be able to compare to the previous bounds, let me try to exemplify with m equals n squared and k being 1/2 of the coordinates. So first we show a lower bound of n to this constant, which is roughly 1.70, 70, not 17. Okay, so that's quite an improvement from the lower bound of Golobash and Radcliffe. Okay, they proved n to the power of 1.17, and this is 1.7. Okay, and the tilde notation here just says that we're neglecting log n terms in the denominator. There's a over log n here, but I only really care about the exponent here. So we were able to prove this lower bound, this improvement over the previously best known bounds. But here is the kicker. We also have an upper bound, which is precisely the same bound or precisely the same exponent. This interesting looking constant is exactly also appears in the upper bound that we get. So up to these negligible log n factors, we solve this question completely, or at least when m is n squared and k is n over 2. Okay, so this is our main result. Or rather, this is our main result for this particular choice of parameters. This is truly our main result, the general case. Here's the bound, the lower and upper bounds that we prove in one equation. So assuming that your family is sub-exponential size, so maybe the number of sets is at most 2 to the power of square root of n, or something of that order, and assuming that the number of coordinates alpha n that you project on is at least maybe square root n or n to the 0.99 or something along that line. So in particular, if it's a linear number of coordinates, then pi, this external quantity, the best number, the most projections you can guarantee, is given by this quantity. So let's see what this is. This is really just the geometric mean of m and n, or rather the weighted geometric mean, weighted by this magical constant lambda, which only depends on alpha. Okay, so it turns out that this is the right answer for the external question, at least if you don't have too many sets and you don't project on too few coordinates. And there's an error in the exponent, which is 0.9999, so almost 1. So that doesn't actually affect the exponent really. So that's the bound. How to make sense of the bound? First, I'll note that this magical constant lambda, while it depends on alpha, it's actually bounded. It's always at most 1, but it's at least 1/2 always, no matter what alpha is. Even if alpha is very, very small, right? Even if alpha is basically 0, lambda is 1/2. So lambda doesn't tend to 0 with alpha. So in particular, the bound that we get here is at least square root of n times square root m square root n. For example, that's a special case of our bound. That's a lower bound. by the way, if m is much larger compared to n, then only this term is significant. So really we get square root of m. That's a very special case of our lower bound, which I don't know a simple proof for. So that's it. You can always get, so let me summarize this very special case of our bounds. You can always guarantee square root m projections if you have a family of m sets and you project on alpha n many coordinates, as long as alpha is not too small. Okay. But of course, this gives the previous result as a special case, right? Because in the special case where m is n squared, then you get here n to the power of 2 lambda plus 1 minus lambda. So that's 1 plus lambda, which happens to be exactly the constant that works for the first theorem. Okay, so everything here is, at least in the exponent, completely tight. Any questions before I move on to talk about proofs? Okay. So let me move on then. So let me first try to prove to you the upper bound. Let's sketch the proof. The upper bound is, once you know the construction, is not too hard. So let me break down what an upper bound means here. So we want to show that there is a particular family, which is of size this parameter m. But if you project on any alpha n coordinates, you always get at most m to the lambda and to the 1 minus lambda many projections. Okay, so for this particular f that we're going to construct, even the best choice of alpha n coordinates won't give you more than this many projections. This is what I want to prove now. Okay. Okay. So here is the construction. The construction is conceptually very simple. You just take random sets, just randomly choose sets of subsets of your universe, take their power sets, and take a union of the whole thing. So a union of random power sets. Okay. So here's the formal construction. So it has two parameters, L and X, which I will choose in a second. So first you choose L sets R1 ... RL random subsets, each of size X. Okay. And then for each one, you take the power set for R1, for R2, etc., and you just combine all of them together into one family. Okay. A union of cubes, so a union of power sets. And it's important that this choice of R's is random. What's also important is the choice of parameters. It's actually crucial. So L, the number of sets, it will need to be m over 2 to the x. We will see why in a second. And even more importantly, the size of each power set, 2 to the x, would have to be m over n to that magical constant that depends on your alpha. If you make this choice of parameters, precisely that choice, and you take this kind of simple random construction, then you're done. You will get with high probability a bad family, a family which doesn't have many projections, even for the best choice of coordinates. Okay, so let me quickly sketch the proof. First of all, I need to show that this family does have, a lot of at least m, more than m sets. Okay, and the intuitive explanation for that, just because the number of power sets is m over 2 to the x, and each power set is of size 2 to the x. So really, the interpretation of what I'm trying to prove here is that these power sets are mostly disjoint. Okay, they don't have a lot of common sets between them. So if you just sum up the number, the size of each power set, you're going to get basically the size of f. That's what we're trying to prove here. So first step is to argue that, okay, the sets Ri themselves are random, completely random, uniformly random of size x. So their intersection, because x is actually small enough, their intersection is quite small. Okay, this is very standard. So again, because the random sets Ri are small, if you intersect any two of them, they're going to have a small intersection, maybe at most, actually much less, 1/4 of the size of each. Okay, that part is easy, but observe the following, because we don't, so the fact that the Ri are disjoint, mostly disjoint, that's nice, but we care about their power sets. Does that imply that the power sets are mostly disjoint? So I claim that yes, but that requires a cute argument. So fix one power set, 2 to the Ri, and consider how many sets in this power set are not unique to it, are actually found in the other power sets. Okay, so we're talking about the set which is both contained in Ri and contained in some other Rj, maybe several Rjs. Now, the obvious fact is that if your set is in the intersection here of these power sets, then in particular your set is a subset of Ri and a subset of Rj. Okay, right? It's both in the power set of Ri and the power set of Rj, which means it's a subset of both, which means that it's a subset of the intersection of Ri and that Rj. But I won't really care about the fact that that this set of ours is a subset of the intersection. I really care about the fact that it's a small subset. Okay, so just from what we said before, the intersection is small. So if you have a subset of the intersection, it's obviously small, at most 1/4 x. Okay, but that's the thing. No matter what Rj you're looking at, our set is going to be of size 1/4 x at most, but it's also going to be a subset of that Ri that we fixed, no matter which Rj you're talking about. Okay, so in short, what I claim here is that each power set contributes a lot of unique sets, in the sense that the sets that are not unique to this power set are a negligible part from the power set. Okay, so the number of unique elements, unique sets contributed by each power set is the size of the power set minus the non-unique elements, which are all of size 1/4 x in a subset of size x. Okay, so this is a sub-exponential quantity in x, so this difference is still roughly 2 to the x. And once you multiply by L, by our choice, then you get indeed m sets in our family, in the union of the power sets. Okay, so that one wasn't hard. The more interesting part is to show the projection bound, to show that if I fix now alpha n coordinates, I'm going to see few projections. So here's what we're going to say. If you project, forget about the expectations here for a second. If you project our family onto this set P of coordinates, then the number of projections is at most the sum of the number of projections that come from each power set. Probably less if there are intersections, but this is an upper bound. Okay, and each power set, if you project a power set onto P, then what you're getting is another power set of the intersection with P. Okay, it takes a second to see why this is true. Again, the projection of a power set is another power set. So we get this bound on the number of projections, which is the sum of all these restricted power sets, their size. Now, notice that both these quantities, f sub p, the number of projections, and this random variable, this sum, which I call x from now on, both of these are random variables, right? Because we have a random process, because the sets Ri are chosen randomly. So this bound immediately implies that a bound on the expectations. So the expected number of projections, but notice that this is an expectation not over P, it's an expectation over the construction, over the randomness in the construction, over the choices of Ri. So the expected number of projections is at most the expectation of this random variable x, which is the sum of independent random variables. And if you actually compute this expectation, it's not completely trivial. You will need a few minutes to see that. Then you will see that each term is actually 1 plus alpha to the x. So instead of 2 to the x, which would be the full power set, it's actually the restricted power set is of size 1 plus alpha to the x. Sanity check, if alpha is 1, so we're projecting on all the coordinates, that means we get 2 to the x, not surprisingly. And if alpha is very small, if alpha is 0, then we get 1 to the x, which is just 1, and that's just the empty set. Okay, so you can check that yourselves. And of course, by linearity of expectation, you get this for each power set. So L times the number of power sets, and this 1 plus alpha to the x. And now comes some algebra magic. If you just play around with our choice of parameters and recall the definition of the magical constant lambda, then after a minute of manipulation, you will get this identity. Okay, L times 1 plus alpha to the x is equal to n times 2 to the x. Why is this algebraic manipulations, why are they actually interesting? Well, the thing is, 2 to the x, so as I said, x is the sum of independent random variables. 2 to the x is the maximum that each of these random variables can get, right? So what we got here is that the expectation is roughly n times the maximum of each random variable. But now if you use the following kind of easy inequality, which is a slight generalization of Chernov's bound, the inequality says that if you have a random variable x, which is the sum of independent random variables, then the probability that it's, I don't know, at least 10 times its expectation is exponentially small in the expectation, normalized by the maximum of each random variable. That's easy enough. But if you plug in what we just found out about the expectation of our random variable x, we get that this guy is exponential in n, which is fantastic because this holds for any choice of p, but there are at most exponential number of such p's. So by the union bound, there has to be a single choice for the construction, right? For the random sets Ri that works for every p. Okay, that's simply the union bound. So for this particular f, every projection on alpha n coordinates has at most 10 times the expectation many projections. Okay, and now you can actually, now this algebraic identity you can check for yourselves, that gives us exactly the bound that we wanted. Okay, so summarizing, the construction is just a union of power sets chosen at random, and the bound that we have on the number of projections is bounded by sum of independent random variables, which is very concentrated around its mean. So concentrated that we can apply the union bound over all choices of p, and that gives us that the expectation is also a bound on the number of projection, but the expectation for our choice of parameters is exactly what we wanted to prove. Any questions about the upper bound? Okay. How am I doing on time? Okay. So I'll try to go more quickly. Next, when I will talk about the lower bound, which is the more challenging aspect of the paper. So first, we're going to reduce the question about projections to a more familiar combinatorial setting. So first of all, we're going to think of our family of sets F as a hypergraph on n vertices, right? Every set in F you can think of as an edge or hyperedge. And in this language, a projection on a set P of vertices, if you think about it, in terms of the hypergraph, this is just the following thing. Maybe I should add size here. You just go over all the edges of the hypergraph and you intersect that edge with P. Okay? So you just intersect all the edges with this fixed choice of P. That's exactly the number of projections of P on F, if you view F as a hypergraph. Okay, so that's a tiny observation. Next, we're going to reduce to the case of a uniform hypergraph, right? There was nothing uniform about the hypergraph F. Different sets can have different sizes. So I will need two pieces of notation, that's all. Standard stuff. So F with an arrow at the top means the down closure, the closure of F. So this is the family obtained by taking all the subsets of each edge. Okay, so again, if I have an edge E in the F, then the closure would also have the power set of E. Every subset of E, we're going to add it into F. Okay, I close downward the family F of sets. Okay, and F choose I, well, notice that this closure naturally is graded, right? It has sets of size 0, 1, 2, 3, etc. Okay, so the closure is a union of these layers. F choose I. These are all the subsets of an edge of size I. Okay, so we need to get used to these two pieces of notation because we're going to use them. So a projection, which means you take the power set of every edge, and this guy, which means sometimes it's called the I shadow of F. This just means that you take only the sets of size I that are contained in an edge. And we're going to use the following fact that I actually mentioned from before, like slide number 3, I think, that there is no loss of generality in assuming that your F is monotone, is closed. Okay, in assuming that whatever F is, it's actually equals to its closure. Okay, this follows from what's called shifting. That's one way to prove this, but I won't get into that. But I was just going to assume that F is monotone from now on. And now I said that I wanted to switch to a uniform, reduce to a uniform hypergraph. So what I'm going to choose is, I'm going to choose the most popular layer. Okay, so I'm going to choose the R that maximizes the size of the layer. And the layer of F, of the closure of F, that has the most sets, the most edges. I claim that this layer is necessarily large. Because it's the largest layer, it has to be pretty large. So let's see why. Let's denote by S the largest size of an edge in F. Since F is monotone, without loss of generality, that means that F contains the entire power set of some set of size S, right? S is the maximum size of an edge. Take that edge, its entire power set is contained in F. So F has at least 2 to the S, many sets, many edges. Okay. Now, H is the most popular layer, so H has at least as many sets as the average layer. But we said that S is the largest number of layers, so F over S is going to be a lower bound on the number of the largest layer, obviously, right? The worst case scenario is that if all the layers are of equal size. I'm actually cheating because it should be S plus 1 because I need to count the empty set, which is actually adds another layer, but never mind that. But as I said, S, from this bound, S is at most logarithmic in F. So we got this lower bound on H. So H, the most popular layer, has size which is, while not all of F, it's close enough to F. It's F over log size of F. So if we don't care about losing logarithmic factors in F, which we don't, then we might as well just work with the most popular layer, hence reducing the problem into a problem about uniform hypergraphs. So that was step 1. So from now on, we have an R uniform hypergraph with n vertices and m edges. But of course, for that uniform hypergraph, you can still talk about its closure, right? You look on all the layers below it, and you can talk about each layer separately. Now, I'm going to show you, it's an easy observation that actually we can express the number of projections if we choose the set that we're projecting on randomly. If we choose P randomly, the expected number of projections, you can actually express it in terms of the size of these layers, weighted exponentially. Okay, and that that's an easy observation. Just requires us to kind of flip the way we think about projections. So the expected number of projections is what? So every potential projection is, of course, a member of the closure of H. Now, for S, a member of the closure, for it to be in the projection, one of the projections, what does it imply on S? Well, it exactly implies that S is a subset of that P that we're projecting on, right? That's exactly the way to get S as a projection, where S, all of the coordinates on S are contained in the coordinates we're projecting on. But you can think of this probability as the expectation of an indicator on the variable, right? Which is 1 or 0, depending on whether you have this containment or not. And now this sum of expectations is, of course, the expectation of the sum. And the expectation of each guy here, if you fix S, what is the probability that it's going to be contained in a random P? Well, each member of S has to be contained in P, and that has probability alpha, because P has size alpha n. So alpha times alpha times alpha, S times, S products, S multiplication. So this probability is basically alpha to the size of S. And we're summing over all the potential projections over the entire closure. But of course, this can be, as we said, the closure is graded naturally. So let's compute this sum layer by layer. So for the ith layer, alpha to the S is actually alpha to the I, right? And then we sum over all the layers. There are most of them. But since in every layer we sum, in the ith layer we sum this constant alpha to the I, then the inner sum is just the size of the layer times alpha to the I. And that's what I wanted to prove. Okay, so the expected number of projections is, if you choose P randomly, can be expressed as this sum, weighted sum, which means that what we read, it suffices for us to find a bound on these shadows, on these layers, on the size of these layers. If you find a bound on the size of these layers, then we're done. Okay. So that's the goal now. After the reductions that we did, prove a lower bound on the size of these layers, and that's actually a classical result in external set theory that does exactly that. It's called the KKL theorem, which says, so I'm not going to. I don't think I have the time, right? Yeah, I don't nearly have the time. So bottom line is that this gives us a lower bound on the number of I subsets of the family H, okay, or the size of the ith layer, and forget about this quantification. The point is that this bound is best possible, and the external example, the external construction, is if you take the complete hypergraph on some x vertices. So where x is whatever. In other words, the worst case scenario for KKL, for Kruskal-Katona, sorry, KK, and is if you take a click, right? If you take a complete graph on just a handful of, like the smallest number of vertices that you can, right? So it's the most dense family that you can think of, the most dense hypergraph. All the edges are concentrated on the smallest number of vertices, and you take all possible edges. Okay, so that's the external example here. But actually, if you think about it, if you take the bound in Kruskal-Katona and you plug it into that expectation that we saw in the previous slide, and you plug it in here, then you actually get a pretty bad bound. And that's bad. That's disappointing because this bound is best possible. And actually, there's a way to see why this is our approach of reducing to Kruskal-Katona is doomed. And the reason is, well, just take the analog of that external construction in the non-uniform setting. So that would be something that we saw before, right? Take the power set over the smallest number of vertices that you can. But the expected size of a projection of a power set, we did that before when we talked about the upper bound, is 1 plus alpha to the x, which if you check is m to the log 1 plus alpha, which is actually much smaller than the bound that we were trying to prove. Okay, so that's a no-go. our approach is doomed, that's bad news. So what do we do? The thing is that actually, while the approach itself doesn't work, this example is not a bad example. It's a bad example for our approach, but not a bad example for the original question, because right, the densest possible hypergraph, which is just a power set or just a clique, that's fantastic because we're talking about the setting where the number of vertices of this clique is much smaller than the number alpha n that we're projecting on. So just instead of randomly choosing your p, your coordinates, be smart about it. Choose coordinates that include those x coordinates, or choose a set of vertices that includes those x vertices, and the rest don't matter. And you will get, your projections is going to be everything. Okay, trivially. So actually, this bad construction is a fantastic construction for the original question. We get many projections, which is definitely the best you can hope for. So what gives? So the issue was that to reduce to Kruskal-Katona, we switched to talking about the projection. Sorry, the expectation of a projection. So we suddenly decided to do something which isn't smart, not choose the best possible p, but choose a random p. Choosing random p just doesn't work, as we just saw. Okay, so maybe there can be, if the worst example for Kruskal-Katona is the best example for the original question, sounds like we have a win-win analysis here. So what we're doing is actually, let's denote by m sub alpha the densest, the most edges that you can see that you see on some alpha n coordinates. Okay, this is basically the number of projections, but you just consider the top layer, just the induced edges, those that are completely contained in P or A in this case. Now, if m sub alpha is close to the total number of edges, okay, by which I mean there is some alpha n vertices that induce already almost all of the edges, then we're done, right? Because then the number, just like we did before, then we'll just project on these alpha n vertices and we'll get 0.99 m, which is definitely fantastic bound, definitely better than n to the lambda, n to the 1 minus lambda. And therefore, we can from now on assume that m sub alpha is bounded away from m. M sub alpha is small. So there are no dense spots. There are no alpha n vertices that span, almost all the edges. From now on, we might as well assume that. But actually, if you think about it, m sub alpha corresponds to, say, if we're talking about graphs, R uniform hypergraphs where R is 2, then this is just what's known as edge expansion. So small set edge expansion. So this is just a notion of quasi-randomness, if you will. And then you might ask, okay, what if I want to prove Kruskal-Katona with the added assumption that our hypergraph is quasi-random, that our hypergraph satisfies this mild quasi-randomness condition, that it has no dense spots. So I'm not going to go into the statement, but here's a rough approximation. Then the lower bound that we get on the number of eye sets, the eye shadow, is m to the beta, which actually is basically the bound that Kruskal-Katona gives you, times this factor, which is large if m sub alpha is small. So the more quasi-random your hypergraph is, the larger this expression is. So you get a better and better bound compared to the classical Kruskal-Katona. Okay. Only caveat is here is that I have this error factor, C, which is actually for our choice of parameters not that bad. I will mention this in a second. Also, while this looks like a bit of a cumbersome statement, it's actually if you just forget about the C, the error term, and you maybe remove this minus T, then this is actually the best possible bound that you can get on the number of projections in this setting. And the proof is similar. It's just a union of random cliques. And the analysis is similar to the upper bound that we saw before. So this is essentially the best possible bound you can get. We call it the sparse Kruskal-Katona theorem. And as for the error term, well, if say m is polynomial, m is not too large, and alpha is a constant, so you're projecting on 1/10 of n, then this error term is 1 over log n. So it's kind of negligible. And if m is larger but not too large, sub-exponential, and alpha or alpha n is not too small, then you can check that this error term is m to the minus liter of 1. So it's actually doesn't dominate the bound that we get, which is m to some constant power. Okay, so as long as we're in this setting, which is the setting of the main theorem, not too large families and projecting on not too few coordinates, then we get the error term is negligible. And now you get, as a corollary, and it takes some algebraic manipulation, maybe it takes 2 lines, you can show that if you plug in the sparse Kruskal-Katona bound into the expectation that I mentioned before, so you plug in the new bound, the new Kruskal-Katona, into this guy, okay, so you bound each layer, the size of each layer by the sparse Kruskal-Katona, which we may, then actually the bound that you get, if you do this carefully, turns out to be this interesting looking bound. So on the right-hand side, we have the constant term c times m to the lambda n to the 1 minus lambda, this geometric mean. And on the left-hand side, we have a geometric mean with exactly the same weights, but now we're taking the average of the average number of projections and the maximum and the densest subgraph on alpha n vertices. Okay, you get that. You will have to believe me. If not, I can show you the 2 lines of calculation. That's an immediate corollary of the new Kruskal-Katona theorem, but that finishes the proof, right? Because here's why. This guy, the expected number of projections, is obviously at most the maximum number of projections, right? So we get that. And this guy is obviously, as we said, at most the maximum number of projections, because this is just the projections that are in the top layer. So what we get on the left-hand side, we bound the left-hand side by a quantity, which is the geometric average of the same number. Okay, so obviously on the left-hand side, we just have this number, which is the maximum number of projections. And on the right-hand side, we have the bound from before, except that for our parameters, the error term c is negligible. So it contributes this 1 plus liter of 1, 1 minus liter of 1 in the exponent, and we're done. Okay, I think I ran out of time. Yep. So here's the derivation from the sparse Kruskal-Katona of the win-win bound that I mentioned. Yeah, I guess I'll stop here. Thank you.
Let's thank the speaker. Questions? I stopped the recording, so